Good afternoon to everybody. The seminar today is Flexoelectricity in two-dimensional materials and is presented by Matteo Springolo. Matteo Springolo is a physicist with experience in flexoelectricity and ab initio computations within density functional perturbation theory. He studied physics at the Università di Trieste, graduating in 2015. He later obtained a master's degree in theoretical physics at the same university. He is currently doing his PhD in physics at the Institut of Material Science of Barcelona within the Theory and Simulation group. In particular, his work is focused on flexoelectricity in two-dimensional materials. So, when you are ready, you can share your screen. And we can start.
Can you see me?
It's still live sharing.
Okay.
Yes, now yes.
Yes. Okay. Hello, everybody. First of all, I would like to thank the organizer for inviting me and giving me the opportunity to present my work. So, in this talk, I will speak about flexoelectricity in two-dimensional materials, and in particular about the out-of-plane and in-plane flexoelectric response due to a flexural deformation. Well, let me begin explaining, describing, or at least try to describe what is the fact that you want to study. In particular, the fact that you want to study is the electronic response of a two-dimensional materials when the materials is bent with a uniform curvature. That means, for example, we are taking a slab, we bend it, and for example, there is a dipolar moment induced out of plane, for example. Let me also specify what we mean, what we refer to as a two-dimensional material. In particular, for us, a two-dimensional material is extended system along the in-plane directions, where we can describe it like a two-dimensional crystal. That means that is described with a two-dimensional Bravais lattice, and that is finite along the out-of-plane direction. But why we are so interested in two-dimensional materials? We are so interested because flexoelectricity is expected to play a prominent role in such materials. First of all, because due to their mechanical strength and their extreme flexibility, and in addition to the dual symmetry that describe this kind of systems, they are allowed to show an unusual amplified electromechanical coupling that are usually ruled out in their biparents. In this way, they can be used for basis in novel devices, especially, for example, in foldable nanoscale technology. But because of the reduced dimensionality of the system, there are some problems that we have to try to solve, first of all. Indeed, as I mentioned, because of the reduced dimensionality, that is the fact that the system is defined like a finite system along the out-of-plane direction, we have an intrinsic anisotropy describing the system itself. Indeed, this means that all the physical quantity that we consider and referring to different directions, by definition, the system are different. That means that, for example, even in the flat configuration, the physical response referring to the in-plane and out-of-plane response have to be defined, for example, by use of different electric boundary condition. For example, the out-of-plane response is usually defined by use of the so-called short-circuit conditions, while the out-of-plane one is defined by use of the open-circuit condition. In addition, as I mentioned, we have some problem still in the flat configuration. Now we are also we want to describe a curved surface, and we have to face another problem. that is the fact that for a curved surface, the bent surface, is not trivial to define what is in plane and out of plane. So how can we define the flexoelectric response of a two-dimensional material? To do that, we decided to represent every fundamental physical quantity we are interested in the communion frame of the band layer. But we have still some problems. For example, if we begin considering the out-of-plane response, we have that there are further problems. Indeed, for example, in bulk materials, flexoelectricity is usually defined by means of the macroscopic polarization that, in the case of a two-dimensional material, can be reduced, for example, can be thought as a dipolar moment, the out-of-plane dipolar moment per unit area. But in the definition of the polarization, there are some ambiguities. In fact, first of all, it depends on the frame. And then this is a problem, because, for example, let me just consider a two-dimensional material and that is not even perturbed, and just think about applying whatever change of coordinates. In this way, we could just change the polarization almost in an arbitrary way, but obviously this is not a physical effect. This is just a mathematical consequence. So this is the first problem that we have to face with. Secondly, in the definition of the polarization, there is a volume factor, and this is problematic because how can you properly define, for example, the thickness and consequently the volume factor in this case of a two-dimensional material? How can you decide how thick is the material? These are, in fact, if we try to apply the definition of the polarization and try to describe the flexoelectric response by use of the polarization, this turns out to be ill-defined. In addition, last but not least, the polarization is not really related with experimental parameters that are usually measured in a typical experimental setup done on a two-dimensional material. So, polarization is problematic, at least for the out-of-plane response. How can you solve it? Clearly, we have to try to find another quantity, another fundamental quantity. Well, the solution comes with the electric potential. Why? Because electric potential exactly solves all the problems that affected the polarization. Indeed, first of all, it is a scalar quantity. That means that the electric potential is invariant under change of coordinates. Secondly, there is no volume factor, so we have removed the ambiguity about the volume. And then, nicely, is experimental measurable. That is what people usually, at least, try to measure in an experiment done in a two-dimensional frame, in a two-dimensional context. So we decide to use the electric potential, and in particular, we define the so-called flexural voltage. That is defined like the constant of proportionality between the voltage drop across the thin layer and calculated by definition of any simple condition, and the curvature, the uniform curvature applied to the material. Now, generally, whatever is the quantity considered in flexoelectricity, we know that the flexoelectric response of material can always split in two contributions. One is the so-called Clandaion contribution that refers, it is equal to the pure electronic response of the system thought as not allowing the internal relaxation of the ions constituting the system. While the second one is the contribution arising from the internal relaxation of the ions. Let's begin now taking a deeper look within the Clandaion response. We find that the Clandaion response, applying the prescription described before, that is describing the quantity in the curvilinear frame of the band layer, we find that it can be written as the sum of two contributions. One is the dipolar moment of the charge density response, precisely as seen in the moving frame of the band layer, plus a previously overlooked term that corresponds or is proportional to the quadrupolar moment of the charge density referred to the flat configuration, to the initial configuration. Now, take a look to the table. Interestingly, very interestingly, we find that there is a systematic remarkable cancellation between the Dipole moment and the metric term, leading to a much smaller electrical response than reported earlier. And then also telling us that considering the metric term is actually essential for to provide a meaningful description of the effect. In order to better explain why the metric term is so important, let me refer to the last row of the table. This is a calculation performed on an hexagonal lattice of xenon atoms, where the xenon atoms are spaced enough to be considered non-interacting. So basically, we're just considering a layer constituted of neutral spheres, and if you think about bending it, clearly the expected response should be zero. I mean, I have a two-dimensional layer of neutral spheres, I bend it whether I want, clearly still I remain in the region where the atoms don't interact, but clearly I shouldn't see any physical response. But if you look just at the dipolar moment, we find that this is non-zero. And is actually related to the ambiguities that I mentioned before. But when we sum again the metric term, we find that the total response, the total Clandine response, is zero. And then we find that in such a case, the response is zero, as it should be, and as we expect. So the metric term is very important to remove ambiguities. The ambiguities coming from the consideration only of the dipolar moment, and to provide a physical result. If we look at the lattice-mediated effect, because of the symmetry of the systems considered, we find that internal relaxation corresponds to an antiphase motion of the atoms that in turn can be seen as two ions described by opposite equal surge. So basically we can see it just like the antiphase motion of an cation and an ion. So we have a more intuitive description of the lattice-mediated effect, where we have that we can write it by use of the effective charges describing the two ions, the flexural coupling, that in this case is the force that is induced on the ions because of the application of the curvature, and instead of the harmonic restoring force. Remarkably, for the systems considered, we find that the ratio between F and A is always more or less the same. And so we can say that the lattice-mediated effect is largely dominated by the effective charges. So, and then this can help in an hypothetical material design. Now, we have taken a look to the Clandine response, and then to the lattice-mediated response. But what about the comparison between the two effects? If we look at the comparison, we find that both the Clandine and lattice-mediated effects, first of all, show a surprising variety in magnitude and sign. And in addition, their magnitude is overall comparable. This contrasts with the common assumption in bike material and in perovskites that the lattice-mediated part dominates. Now, we have provided a theory and a computational method to calculate the out-of-plane flexoelectric response of a material. And we have analyzed the Clandine and lattice-mediated effect, and we have provided some results. But who assures us that the method and the computational results that we provided are correct? Clearly, in principle, nobody. But fortunately, there exists a physical system that leads to the same local geometry of a band layer. And this is a nanotube in the large radius regime. Indeed, it is well known that the voltage drop between the inner and outer sides of a nanotube is given by the expression that you can see here, where R is the radius describing the nanotube, and then its inverse is the curvature describing the cylindrical geometry of the tube. Then the constant of proportionality between the voltage drop between the two sides and the curvature has to be the quantity that we defined and that we calculated. So nicely, such a system provides a possible consistent check to benchmark our method and then the validity of our results. So what we did was perform explicit calculation on boron-nitride nanotubes of increasing radius. And particularly, we did it at the lambda ion level, just to reduce the computational effort. The brute force calculations, the brute force method, show that there is an asymptotic convergence to our linear response method. But at the same time, highlights the advantage of our method, because indeed we can see that the slope of the rate of the convergence is quite slow. Indeed, even for the biggest nanotube considered, that is constituted of more than 100 atoms, the deviation with respect to the convergence value is still about 10%. Then we can see, as I mentioned, the advantage of our method, that conversely provides an optically converged value with a much less computational effort. So we just described the out-of-plane response, but actually we recently predicted an in-plane response. In this case, we describe the in-plane response as the short-circuit curvilinear polarization response induced by the curvature. So, similarly to what we did in the out-of-plane case, where we used in such a case the out-of-plane, the voltage, the flexural voltage, and then the voltage drop response. Here we define the constant mu, that is defined like the constant of proportionality between the in-plane polarization and the curvature. Now, conversely to the out-of-plane response, that is actually an effect that we can call universal, in the sense that is basically and in principle allowed for any material, regardless the symmetry describing the material, and particularly the material in an insta-flat configuration. We have that the in-plane response is an unconventional effect, in the sense that it depends on the symmetry of the system, or actually depends on the lack of symmetries of the system. Indeed, we have that two conditions are necessary in order to see a non-zero in-plane response. The first one is the lack of a z-oriented mirror plane. The second one is the lack of XY inversion symmetry. Now, despite while our method is valid in the most general case, I mean, we could apply it to whatever material with whatever symmetry we want. Here we focus on a class of materials that also have the highest symmetry compatible with the two criteria mentioned above. In particular, we considered trigonal materials that also are described by a z-oriented free-fall axis, a space inversion symmetry, and a vertical mirror plane. Here I report a sketch of the material considered, where we can recognize the free-fall symmetry, and for example, the space we cannot recognize the space inversion symmetry because we are looking from above, and also the vertical mirror. Now, within the free-fall symmetry, we find that the polarization can express in a very nice way. In particular, we can represent we can represent it in the frame lambda 1, lambda 2, that is defined like the frame where the first vector is the bending direction, while the second one is the orthogonal vector to the first one. And when in this case, the same bending direction is uniquely identified by the angle theta. Here defined like the angle between lambda 1 and the x-axis. So in this way, we find that the polarization response can be written as an explicit function of the angle theta defining the bending direction. We find, looking at the expression, looking to the expression, we find that actually the polarization continuously rotates with the bending direction, and in addition is invariant under rotation of the kind m2 pi over 3, where m is an integer. This is consistent with the threefold symmetry of the flat layer. In addition, we find that the polarization magnitude is actually independent with respect to the bending direction. Here at the side, we can see indeed the kind of behavior of the polarization while changing by the angle, by use of the angle theta, the direction of the bending. Again, we can look to the comparison between the clamp diode and lattice mediated effect, when we find that first of all there is a systematic change reversal between the clamp diode and lattice mediated effect, and in addition, similar to the previous case, that is the out-of-plane response, we find that their magnitude are overall comparable, except, for example, to the case of rhodium triodide, when the clamp diode response is 1 order larger than the lattice mediated effect. But maybe the most interesting finding in this case is that the in-plane response turns out to be much larger than the out-of-plane one, and in many cases almost one order larger. So even if this effect, that is the in-plane effect, is an unconventional effect that is active only in a certain class of materials, we find that it can be much useful than the previous one. Now, we actually realized that the quantity that we defined and studied has a very important physical implication. Indeed, we find we can understand that a nanotube made of this class of materials and constructed by bending one of these materials can actually be endowed with a spontaneous axial polarization that is supposed to be given by the expression that you can see here. So, in order to verify such a conjecture and consequently also to verify and again benchmark the validity of our method, we perform direct calculation on the axial very phase polarization of zigzag thin tissue 5 nanotubes, where a net polarization is supposed to exist along the axial direction. We found that the calculations on the nanotubes are in perfect agreement with the linear response, and then again, in this way we can assure the validity of our method and of the computational results. Sorry. Now, actually, the example that I just presented is a peculiar case of a more general consequence. Indeed, we recently realized, and this is a really recent result because actually we realized such a thing just last week. We find that the quantity considered is very important to describe the polarization texture, that is in general the polarization field within the material of arbitrary ripple structure. Indeed, we find that even when the curvature is not uniform but described, but is, for example, changing in space, that means having a local curvature, the quantity that we study can be still used to derive the polarization field. Here I report, for example, two examples. The first one is a periodic deformation corresponding to the superposition of three sinusoidal deformation in turn described by three with vector that are rotated each other by 120 degrees. And then the recast, is described by a threefold symmetry. While the second is the application of a single Gaussian bump. That it means just perturbating in one single point the material by a Gaussian kind deformation. In particular, we find that the polarization field is not trivial at all. And indeed, for example, in the first case, we find that the resulting field corresponds to a honeycomb kind lattice of vortices. And the second one corresponds to this strange figure that where both of them are non-trivial figures, but they can actually be described. They are actually specific topological figures. When indeed the first one is the so-called vortex that is described by a characteristic topological number, that is the so-called winding number, and in particular by a winding number equal to 1. And the second one is a so-called anti-vortex described by a winding number equal to of 2. So we find that the quantitative study is very important to possibly describe what we could call topologically flexoelectricity. That means try to describe the topological non-trivial textures of an arbitrary called two-dimensional structures. Where in this case I reported just the in-plane polarization field. So we can conclude saying that we managed to develop and provide a general method to calculate the out-of-plane and in-plane flexoelectric response of a generic two-dimensional material, and that we found that both of them can be split in a purely Clamp-Dion lattice-mediated contribution. Particularly in the out-of-plane response, and in particular in the Clamp-Dion response referring to the out-of-plane response, we found a previously overlooked metric term that is actually essential to a meaningful physical description. In addition, we find that generally for both out-of-plane and in-plane responses, the Clamp-Dion lattice-mediated contribution are overall comparable. And we find also that they are described by a surprising variety of magnitude and sign. We then calculated the in-plane response and found that its magnitude is insensitive to the band migration, and that its direction actually rotates with a behavior that is compatible with the threefold symmetry of the system. Finally, we found that the out-of-plane response turns out to be much larger than the in-plane one, and in many cases up to almost one order larger. Finally, we presented the physical implications of such an effect in describing the general polarization field in a two-dimensional structure. Also, we benchmarked our method by use of calculation, by means of calculation in a set of nanotubes. Thank you.
Well, thank you for your very interesting and nice presentation, and for sure for accepting my invitation today. So now it's time for questions. We have one from the Ancos in the chat. I can read for you. Thank you for the talk. Did you study the flexoelectric response only static conditions or also dynamic?
No, only steady conditions.
Maybe we have another one from Maria Elisabetta. She's writing, maybe, I think. Well, in the meantime, I have a curiosity too.
Yeah.
Well, okay, we have the question. So, before Maria, how does the temperature may influence the system?
Yeah. Well, clearly the temperature can change all the. I guess clearly I should think about it. that really can change, I think, well, also with temperature, I think that is related with dynamic, I guess, because in this case, considering temperature, we are going to introduce filter parameters, and I think I'm not sure, because I have to say that all the implementation is done by the already existing implementation of flexoelectricity as provided by Abinit, that is done within the density function perturbation theory by long wave analysis. Now, I'm not sure if temperature introduce a different different way to treat the phonons, besides maybe other effects on, for example, the electronic clouds, and then on the movement of the ions.
Thank you. We have another one. How does the flexoelectric effect in three-dimensional materials compare to the piezoelectric effects? Would piezoelectric effects be already included in your calculations?
This is a very good point, because well, I can show a slide. Actually, piezoelectricity here is is more important, because actually in a two-dimensional material, the fact is that enters also the so-called local piezoelectricity. I mean, for example, usually in bulk materials, we consider just the so-called genuine flexoelectric response. That means that we are just considering one part, only the macroscopic effect. When we consider a system with a reduced symmetry, actually there is a further contribution that comes from the local piezoelectricity. This is very important in this kind of system. It actually is really related with the system. Indeed, let me show a figure if I can. Can you still see the presentation, right?
Yes.
Okay. So, well, sorry, this okay. Actually, let us consider, for example, a system constituted of that corresponds to a bilayer. In this case, let's consider a bilayer of a boron nitride. Okay, where we have two possible. We have a different several way to stack the two layers constituting the bilayer. Okay, but let's consider, for example, two kind of a stack. One is the so-called AA, where the two layers are just one above the other, and they have the same orientation. And then consider AA prime stack, where we have again two equal boron nitride layers, but rotate each other by pi. Okay. In this case, in such a case, if we consider the two layers distant enough to be considered non-interacting, actually the flexoelectric effect is exactly given by use of the piezoelectric response of the single layer. In particular, one can show that the quantity mu that we defined in the presentation, that is the in-plane flexoelectric response of the two-dimensional material, can be exactly written like through the in-plane piezoelectric response of the material and the distance, the interlayer distance of the layers. So here we find that the kind of stacking is very important, and that's why actually it is also related with the symmetries that I mentioned before, because it's very important the kind of symmetry, or better, the lack of symmetry of the materials considered. Indeed, we can see that when we bend the material, basically the upper layer. Also, let me say that here U refers to upper and the L to lower. Okay. Then the above layer feels a negative in-plane strain, okay, uniform strain, while the lower layer feel an expanding strain. So we have that basically the overall effect can be written like the sum of the two single effects, but responding to by linearity in an opposite way. So since they reply, let's say, in an opposite way, If we stack them with the same direction, the overall effect is 0. Why? If we stack them with an opposite direction each other, we have that the two singular response sum, and then with the overall effect is non-zero. So actually, piezoelectricity, also, indeed, the symmetry of the piezoelectric tensor comes exactly, for example, I mean, they are compatible with the symmetry of the, in this case, of the single layer. So the piezoelectricity is very important to the overall effect in this case.
Thank you. We have another one from Jean-Paul Neri. Thanks, Matteo, for the talk. Why had people overlooked the metric term? They sort of assumed that they could consider it flat from point to point or something like that.
Can you repeat, sorry?
Why had people overlooked the metric term? They sort of assumed that they could consider it flat from point to point or something like that.
Why did people overlook the metric term? Well, actually, because I guess then I'm not sure about it clearly, since people didn't see it. The fact is that, as I mentioned, people always tried to define flexoelectricity. I mean, if we speak about first principle, people always tried to look at the flexoelectric response in two-dimensional material by use of the polarization. And well, first of all, and indeed in lecture we can find some that there is a lot of disagreement about the reported values. And this is because actually also the definition of the thickness of the material that I mentioned before. So I think that in this case, the fact that people overlooked the metric term is because people always consider just the polarization, that despite the fact that in principle every object that we define in a different curvilinear frame clearly brings with him a geometrical term. But the metric term that I show comes from the linear variation of the vacuum permittivity. That it means that it comes from the change, the curvilinear representation of the Poisson equation. So if you think about the Poisson equation, we have that the Laplacian of the voltage drop multiplied by the vacuum permittivity is equal to the charge density. Well, if you properly do the change of coordinate, you find that actually the vacuum permittivity in a curvilinear coordinate is no longer a scalar, but actually is a tensor. And this is a tensor that is related with the metric tensor of the deformation. So I guess that's why people didn't recognize it before, because people were looking to a different quantity. So you cannot see the metric term if you don't expand, if you don't expand at the first order the curvilinear representation of the Poisson equation.
Thank you. Well, there is a message from Professor Teddy that tells that it's not her field of research. She has no question, but appreciate the clarity of your talk. And after that, we have another one. More generally speaking, do you think that at this scale it makes sense to talk about polarizability? Or is local potential really the only way to study two-dimensional materials?
The second part, sorry?
Or is local potential really the only way to study two-dimensional materials?
Okay. About the first question, yes. Well, depending also on the direction that we consider, I would say yes, makes sense about speak about polarizability. Yeah, I think so, because basically, I think that it can relate with the quantity that we studied, depending on the definition as well. Basically, if we manage to relate to it with, for example, in this case, the voltage drop that we define, or for example, in the case of the in-plane polarization, the in-plane response, sorry, with the polarization, I think that we can clearly could be harder to properly define it. But for example, I think that in the first work, that is the one concerning the out-of-plane response, we actually noticed that, for example, in some way, the out-of-plane response is related with the polarizability of the material in such a direction. we can establish a sort of connection, because also the amount of response is related with the thickness in certain sense, in some way, of the material. And of course, the polarizability, if I'm wrong now, is also in some way proportional to the thickness of the material. About the second question, it's a very interesting question, because actually, well, we can reduce the two quantity, at least for this component, not in general, because indeed I want to stress that we are speaking just about the in-plane and out-of-plane response due to effects of deformation. To arrive to a general description like because of other deformation is hard, but actually the two quantity that we studied can, you can derive them by using, for example, the electric displacement field. For example, let me clarify that the out-of-plane response can be obtained by applying the open circuit condition, that is calculate the variation of the electric potential at a fixed electric displacement field. Conversely, the short circuit, in this case, so the inclined response is calculated by calculating the response of the electric field displacement at a fixed potential. In this case, it reduces to the polarization. But actually, you can define it by use of the electric displacement field. Sorry.
Thank you. So, if there aren't more questions, just a curiosity from my side. This is not my research field for sure, but just if you can tell us something about, well, you performed calculations, but I think probably there are some experiments that can fit with your calculation. So if you can tell something about.
Yeah, actually experiments are a problem in the sense that in literature there are, you cannot find so many experimental results because of the difficulties in extracting the relevant information in an experiment regarding two-dimensional materials. But for example, recently we also tried to propose a kind of an experiment, actually two kinds, but let me first of all describe this one. That is, for example, we could try to measure the flexoelectric response, in this case, the in-plane I'm referring in this case to the in-plane one, by use of the following experimental setup. That means try to deposit the two-dimensional material on two electrodes that in turn are laid on a substrate, and where the two electrodes are separated by a distance cell. In this case, we have that the energy function can be written by use of the so-called bending modulus that is related with the curvature, and the applied electric field and the curvature, where the coupling about the electric field and the curvature, by definition, is exactly the quantity that we studied in our work. So clearly we can, and also let me specify that in this case we are assuming the layer, the deposited layer, as non-interacting with the substrate. Actually, many times it does because of van der Waals kind of forces. Let me begin just considering it like non-interacting. So when we apply electric field, for the effect that we mentioned, the layer is supposed to bend, and by a minimization of the energy functional, the curvature is supposed to be given by the expression that we can see here, where is k equal to E mu over B. But at the same time, in the small curvature regime, where compared with the parameter L, that is a geometrical parameter of the setup considered, we find that we can calculate also, we can extract the maximum bending distance. At the same time, such a distance, the bending of the material can be measured by use of the so-called the piezoelectric force microscopy, and then we can take an image of the sample. By use then, this means that by use of the applied electric field and the geometrical parameter L described in the setup and measured curvature, we can extract, hypothetically, we can extract the flexoelectric response that we defined and described in the article. So basically, we can extract such an information. Also, there is a second way to do it, even when the material is interacting with the substrate, that by use of the so-called second harmonic generation. I can say about it something about it, but maybe it's already I'm speaking too much about it.
No, it's interesting. So, are there more questions or curiosities? Seems not. So, thank you again for the presentation, for being here today. And let's move on. Next Thursday is the last seminar of the year, and will be a biology one. Title is Maintain Your Thinking Tape, a way to improve memory loss in Alzheimer's disease, presented by Dr. Catherine Lawrence. So, see you next Thursday.
Thank you.
Bye.
Bye.
Thank you very much. Bye-bye.
Bye, thank you.